Hello and welcome. In this video, I'm going to speak about two of the timing protocol used in the industry these days. One of them is going to be NTP, Network Time Protocol, which has been around for a very long time, since 1985 as a matter of fact. And the other one is going to be PTP. That one, of course, is not new as well. It has been around for more than 20 years, but it is much newer than NTP, and it has some features that you might really want to use that in your network. Specifically, some of the operators, mobile operators, are one of the users of that protocol here. So what is NTP? Why would we really need to have timing in our network? Let's say that I want to troubleshoot some of the devices in the network. I don't have any correct timing set for the logs that I want to read and check what the problem was in the network that caused this to happen. So I would not really understand the order of things that have happened and led to this catastrophe in my network. So NTP is going to come into play. All of the devices are going to have the same timing set on them. All of them are going to be synchronized against one source, and that source is going to be my reference point for time. And of course, the good thing about NTP is I can just introduce time zones. This means that if I have a network globally dispersed, or maybe around the country that has multiple time zones in that, then I would not really have any problem understanding the timing on different devices around these networks. So, like I said, NTP is one of the oldest internet protocol still in use today. The purpose is going to be the minimizing difference in time, which means that all of the devices are going to be set with the same time reference, or maybe multiple time reference that talk to each other and kind of synchronize with each other. And we have some features. The most important one is the difference is going to be a few milliseconds from UTC. Why would I say milliseconds? That's because I have to consider some delays, specifically the delay for the cables, for example, that have been run across the nation. For every 1,000 kilometers, you should just assume that there's a 5 milliseconds of delay, and that's going to accumulate, of course. If this is, for example, a 10,000 kilometer cable, then you have to just account for 50 milliseconds of delay here. Or easier one, of course, is going to be this. For 1,000 miles, you are going to have 8 milliseconds of delay. For 10,000 miles, this is going to be 80 milliseconds of delay. And that is the difference that you have between the time of different devices if all of them are receiving the timing information from the same source. So a few milliseconds is not going to hurt. That's very good. But in some cases, of course, we need to have even more precise timing than this. But here, inside the LAN, of course, that's going to be much less than this. So inside the LAN, we are going to have less than, let's say, 1 millisecond. Better than 1 millisecond accuracy inside the LAN. That is because the proximity of the devices is very much high in here. But in LAN, of course, you're going to have something like tens of milliseconds, but not too drastic. NTP is a client-server protocol. We have peer-to-peer relationship between different servers, but as a matter of fact, in the end, one of the devices is going to receive, that is, this one, for example, a client is going to receive the timing information from this server up here. This server, of course, might be client to another server, and we can have a kind of a hierarchy of servers in here. And what we have is the stratum value is going to tell us that whether this is going to be the topmost server in the network, maybe an atomic clock, which we are going to synchronize against that, or this is lower in hierarchy. For example, if I configure something, the stratum value could be at most 15 or 16 as a matter of fact, and 1 is going to be the least amount. And I would say, for example, in my network, this has a stratum of 8, and I'm going to configure this in the 8th level from the first atomic clock that I have synchronized with. But anyway, like I said, this is kind of a client-server relationship that we are going to have between the devices. Also, you should know that NTP has different versions. NTP4 is the most recent one, and it is very much compatible with version 3, which was very common a few years ago. But what about precision time protocol? This one is going to be more precise. And when we say more precise, over the internet, we are talking about less than milliseconds, and inside the network, microseconds, of course. And in some of the, for example, financial transactions, specifically what we call it high frequency trading, this is going to, create kind of a fairness between different companies. And that's very important. For mobile phone tower transmissions, this is going to be important. Also some other areas that you can see in here. All of them are going to be applications for PTP. And like I said, most of the time, we just refer to PTP as the protocol of choice for these two applications. So what are the components of PTP that we want to have? We can have different types of clocks, of course. And there is a master-slave architecture. One of the most important components are going to be grandmaster. Grandmaster is going to be the top device in the network, which is going to be the source of timing for others. Like I said, we have ordinary devices, ordinary clocks. That is the devices that are going to serve either as source or as destination, which means that they can work as master and or a slave. And also we have boundary clocks that connects multiple networks to each other. The other one, the master-slave architecture, like I said, is present in here, but we have some process in understanding the PTP, which we use messages for that. And let's say that, for example, in this process, I'm going to have this switch in here, which is going to be the source of the messages. Let's say this is grandmaster. This is going to send the information to this switch. This switch is going to send it to another switch in here. So that is S1. That is S2 in this network. So this first switch is going to send a message to the first switch, which is here. Switch 1 receives the message, the timing message, and let's say that the time says, and I'm going to be super rough. Like I said, you should go for microseconds, but let's say that I'm just being very rough, and I'm going to say the difference is seconds. So I have received a packet that says my time is 10:51, okay, and 51:25 seconds. So switch 1 is going to say, okay, you sent this to me. How long does it take for the message to get to me? Because I have to add it to this. And when I receive this, as a matter of fact, it is not 10:51:25. So it sends a message, which is called a delay request message to grandmaster. So in that delay request, what we have is we have just sent this. I said, for example, this is 10:51:26, for example. And when did you receive it? Grandmaster, of course, is a source in here. So it just receives the message, and it checks and sees that it is 27 seconds. And it says, okay, 1 second of delay was here, and it responds to server 1 using delay response message. And so switch 1 is going to understand that the delay between it and the grandmaster is 1 second. So whenever it receives a timing packet, which is a sync message from this grandmaster, it's going to add 1 second to that. And it knows that now this time is accurate because it has received this timing from the upstream switch in here, which is the grandmaster. The same thing is going to happen here. So switch 1 is going to forward the message to switch 2. Switch 2 is going to receive this, and it's going to ask switch 1, okay, what is the delay between me and you? So basically, again, switch 2 is going to send a message. It's going to say, okay, in my time it is 10:51:29. So when do you receive this, and how much is my delay? Switch 1 is going to receive it at, let's say, 31, and it's going to send a response here that your delay is something like 2 seconds. So it understands that whenever it receives a time from switch 1, it's going to add 2 seconds to that to have the precise time on that. So based on this simple process, each one of these switches are going to be configured with the most precise timing. Like I said, I went with seconds, but we are talking about microseconds, so that is very important to understand. So the delay is going to be added, and also this delay is going to be accumulative, because now from Grandmaster to switch 2, we have just added this delay and added this delay, and switch 2 has received it with its own delay between switch 1 and switch 2, and it knows that the difference is this much, and it's going to configure it in here. We can have multiple Grandmasters in our network. Let's say, for example, another one is here, GM2, this one GM1. Maybe this one is connected directly to switch 2. One of them is going to be in backup mode. One of them is going to be in active mode. In case the active mode goes down, the backup one is going to come up and start working in the network. Again, PTP has more to talk about, but like I said, I wanted to just give you an overview of the protocol and the type of messages that go through the network, and based on that we can understand what time it is. You should know that this is again another standard that a lot of devices, network devices, including OcNOS devices, support, and you can just enable it in your network and use it to your benefit. I hope this has been informative for you. See you in next videos.